Prescription glasses appear simple. Two transparent lenses set in a frame resting lightly on the nose, supported by arms that extend over the ears. It feels like the only logical configuration. But that form is the result of centuries of trial, anatomical compromise, and optical precision. Before wearable glasses existed, vision correction was handheld. In the late medieval period, early lenses were mounted in simple frames that had to be held in front of the eyes. They were useful for reading, but impractical for movement. You could not walk or work while holding them steady. The first wearable designs balanced two lenses on the nose without arms. Known as pince-nez, these frames relied on spring tension pressing against the sides of the nose. They stayed in place if the wearer remained still, but movement exposed their limitations. Turn your head quickly and they slipped. Sweat or oil reduced grip. Extended wear caused discomfort. Other variations tied lenses to ribbons or cords that looped around the head. These provided stability but created pressure points and visual obstruction. The core problem was alignment. Corrective lenses must sit at a precise distance from the eye, known as vertex distance. They must be centered in front of the pupil to avoid optical distortion. They must remain stable during motion. Even small shifts can alter clarity. The aha moment arrives when you realize that glasses are not just holding lenses near your face. They are holding them in exactly the right place, consistently. That requirement narrowed design possibilities dramatically. The breakthrough came with the addition of temples, the arms extending backward from the frame. These arms hook gently over the ears. They convert the head itself into a support structure. The bridge rests on the nose, distributing downward force. The temples apply slight backward pressure, counterbalancing gravity. The ears act as stabilizing anchors. This creates a three-point support system. Two contact points behind the ears, one across the nose. It is not arbitrary. It is geometry. A three-point system provides stable positioning without requiring tight compression. Too much force causes discomfort and headaches. Too little, and glasses slide forward. The shape of the bridge evolved alongside this understanding. Early bridges were rigid and fixed, but human noses vary in width, angle, and contour. Adjustable nose pads were introduced to accommodate these differences. Nose pads allow micro adjustments in height and tilt. They also distribute pressure across a larger area, reducing discomfort during long wear. The weight of the lenses shaped frame materials. Early lenses were made of glass, heavy and fragile. Frames were metal or tortoiseshell. Weight placed strain on the nose and ears. As plastics advanced in the 20th century, lighter lenses and frames reduced this burden. Polycarbonate and high-index plastics allowed thinner, lighter lenses for strong prescriptions. The reduction in weight expanded design possibilities. Frames could be larger without becoming uncomfortable. But lens size still interacts with optical alignment. The optical center of each lens must align with the wearer's pupil. If the pupil is not centered relative to the lens, distortion or strain can occur. That is why opticians measure pupillary distance. Even when frames are oversized for fashion, the prescription portion of the lens is centered precisely. The visible lens may appear wide, but the corrective zone is positioned exactly where the eye needs it. This reinforces the realization: glasses are alignment devices. They must hold transparent materials at a specific angle and distance relative to moving eyes. The tilt of the frame matters as well. Glasses are not vertical slabs. They tilt slightly inward at the bottom, a position called pantascopic tilt. This aligns the lens surface more naturally with the eye's line of sight during downward gaze, such as reading. Without this tilt, the lower portion of the lens would distort peripheral vision. The frame's curvature across the front also matters. Some frames wrap slightly around the face. This curvature reduces peripheral gaps and improves stability. However, excessive wrap can alter optical geometry, requiring specialized lens shaping. Trade-offs appear constantly. Larger lenses increase field of view but add weight. Thicker lenses increase durability but reduce aesthetic appeal. Slimmer frames look minimal but may flex too easily. The hinge connecting the temples to the frame front is another critical element. It must allow folding for storage but remain rigid during wear. Spring hinges were introduced to allow slight outward flex, accommodating wider heads without permanent deformation. This reflects human variability again. Heads differ in width and shape. The frame must adapt without causing pressure points. Even the end tips of temples, often coated in soft plastic, serve a purpose beyond comfort. They increase friction against skin, preventing sliding. Gravity remains the persistent force shaping the design. Glasses must resist sliding downward along the slope of the nose. The bridge angle and nose pad friction help counter this. The backward pressure from temples balances forward torque. The entire frame functions as a lightweight balancing mechanism. Before modern frames, vision correction was situational. Monocles corrected one eye but required facial tension to hold in place. Pince-nez were temporary solutions. Head straps were cumbersome. The addition of temples created permanence without discomfort. It allowed people to move naturally, to walk, bend, turn, without losing alignment. Human behavior influenced frame evolution profoundly. People wear glasses for hours daily. Frames must be durable enough to withstand removal and placement repeatedly. They must survive being set down, bumped, or dropped. The shape of the lenses themselves reflects optical requirements. Round lenses were historically easier to grind evenly. Over time, rectangular and other shapes emerged, influenced by fashion and field of view considerations. But even in varied shapes, the alignment logic persists. The lens center remains aligned with the pupil. The bridge remains positioned to distribute weight. The temples continue to anchor behind the ears. Modern innovations like rimless frames reduce weight further but retain the same structural geometry. Even contact lenses, which eliminate frames entirely, replicate the same alignment principle by resting directly on the cornea. But contact lenses introduce their own trade-offs: maintenance, dryness, risk of infection. Glasses endure because they balance correction with simplicity. They do not invade the body. They are removable. They require no surgery. The moment of realization deepens when you consider that glasses must correct invisible optical errors, myopia, hyperopia, astigmatism, through precise shaping of transparent material. The frame's job is not decorative. It is structural support for optical accuracy. If the lenses shift even a few millimeters, clarity changes. The design must prevent that. Invisible design often manifests in stability. Prescription glasses exist in their current form because they provide stable optical alignment using the head itself as a support structure. The ears and nose become load-bearing components. The lenses float in front of the eyes at exactly the right distance, angle, and height, and the wearer rarely thinks about it. When glasses fit well, they disappear from awareness. When they slip, pinch, or distort vision, discomfort becomes immediate. That contrast reveals how precisely tuned the standard form has become. Even as styles change, thick frames, thin frames, oversized, minimalist, the underlying architecture remains consistent. Two lenses connected by a bridge, two temples extending backward, three-point support, balanced against gravity. It looks inevitable. But inevitability is often the product of convergence. After centuries of experimentation with straps, clamps, and handheld lenses, the current design proved most efficient at solving the alignment problem. Prescription glasses are not shaped around fashion alone. They are shaped around the physics of light and the geometry of the human head. And perhaps that is the quiet triumph, a device that corrects invisible distortions while remaining almost unnoticed. Invisible design at its best does not draw attention, it restores clarity and then steps out of the way.